Hello guys, this is for FBC student communication 1. Before we start, if you haven't subscribed, please go and do so. Thank you for that. Again, at the background, if you hear some sound, that means it's my son making some noise. I was saying this for com 1, and for noise, a short summary of that. Again, I'm really sorry for that. It's late, but I hope you accept my apology because it's late. I know the exam is tomorrow morning, so we just go briefly about a summary on noise. So we definitely saw in class, we talk about negative noise, we talk about positive noise. We say negative noise was that undesired noise that is generated by the circuit element, and the positive noise is actually the noise we are reading at the output of the antenna. That's the positive noise. So mostly in radio astronomy system, the desired output, let's say this is signal going in, so this the element circuit here, the diagram and everything inside, amplifier, bit amplifier, circuit, the input generator and everything. This is the output. So for astronomy system, what we read here at the output is actually the positive noise called P0 or N0, which is actually the receive power noise. We talk about the type of noise. We said we have flicker noise, we have plasma noise, we have quantum noise, we have thermal noise, which as well called Johnson-Nyquist noise. Okay, so the thermal noise can be called Johnson noise or Nyquist noise. We talk about the noise with a flat frequency spectrum. If you remember, I explained that noise is when we have a flat frequency. That's the noise with a flat frequency spectrum. For example, when you put a fan on or AC on, that noise you hear shh continuously is called flat noise. So it's called noise with flat frequency spectrum, and it's called white noise. That's a white noise. Okay. Yeah, here you remember we saw this. Let's say this VT is the resistor. So this is a random voltage generated by a noisy resistor, and we represent it in terms of diagram. If you know, this is a normal sinusoidal curve, but when it's noisy, it goes this way. So this noisy resistor, here we have a temperature here, of course, coming in, and here we have a output. To find the voltage of this noise, we know, I remember I gave you the formula. The voltage was K HFBR over exponential HF over KT minus 1. And we say if you approximate this one, if HF is greater than KT, sorry, very smaller than KT, then this approximation will give us HT over KT. So when we do that, we found out that the voltage equal root square of 4 KTBR when you do the substitution here. Okay, so this is the voltage due to a noisy resistor. So this is the voltage we have, which is mostly used for analysis. Now if you receive this one, if you replace this one by Thevenin, if you replace this circuit here by either ideal band pass filter, means we have a bandwidth. Okay, here we have the output, here we have the resistor and a voltage. This is R, this is VN. We have here, we add an either band pass filter, and this is the output. So if you find, they're asking you to find the average, let's say the maximum power is Vn over 2R square times R. You will give Vn square 4 times VR 4R, sorry, which is KTB. And I told you before that this received power can be noted as N0 P and what have you. So this power here is actually what we capitalize on here. So here is N out or P0, here is Ni or Pi. So the maximum power we have at the end of the receiver here is KTB. Here again, this circuit will replace with this to have that. Okay. Oops. These are the paper I used for you before. So let me look for another paper. So we said that P was equal to KTB. So this was for a normal resistor, noisy resistor here. Now if you have this one replaced by a noise amplifier, note that this one can be N as well. If you have this one replaced by this one, here goes like this. So this is the gain, this is the amplifier, this is the equivalent temperature, this is a noisy amplifier. Okay, amplifier. Here the output, we have this, we have the resistor. So this the resistor. So this one is replaced. If you remember, this dot means we replace it, we assume it is a new diagram. So here is the output noise, here is the input noise. Since we have an amplifier now, what will be the output here? N0 will be K T, the equivalent temperature we have in here, times the gain of the amplifier times the bandwidth. Okay, so this is basically what it is. When we don't have an amplifier, we have this. When we have an amplifier, we have this. Okay, we talk again about the Y factor. So I'm done with this. We talk about the Y factor. We know in practice we cannot have in practice 0 Kelvin at this level at the input of a diagram or an input of a circuit. So that's why we use the Y factor actually to find the output at the end of the receiver here. And for that we have the diagram of a Y factor, which is this way. Here we have N1, here we have N2, here we have the gain, we have the bandwidth, we have the equivalent temperature. So when this one is connected here, this T1, it can be hot or cold. So this is my, and here we have T2, which is cold. So if you want, so these are the receive power at the end of the circuit here with the reflected power we send at the beginning. So if we need to find N1, of course we have the input power here added to the equivalent temperature and the equivalent value of the amplifier, means N1 is equal to J K T1 here times the bandwidth plus this one J K B equivalent temperature when we are looking for N1. If you are looking for N2 now, we disconnect this one, we connect this one, we have N2 J K T2 times B plus J K B T E. So that's the output, the noise power at the end of the receiver here. And again, you remember, for this Y factor to exist, it should be greater than 1. So what the formula of the Y factor is N1 over N2, the N1 over N2. If you call this one 2, it should be N2. If you call this one 3, it should be N3. So it's N1 over N2, which is in fact TE, T1 plus TE over T2 plus TE. And this one should be greater than 1. So for the Y factor to exist, it should be greater than 1. So if you simplify this one, if you write now TE function of Y, we have TE equal T1 minus Y T2 over Y minus 1. So this for the Y factor. We saw the noise figure as well. Remember the noise figure is F we say it was xini over s0 n0, and s is the output signal power, which is j over so. I will not take too much time here. I will just go directly to the conversion we have done as well. I'll show you some small conversion. If you remember, we saw as well, we talked about cascade. If you remember, I don't want to go over 10 minutes, but I'm already there. We saw the cascade diagram. I would like you to check at this one as well. So let me go straight forward to the conversion. Okay, if for example we have a noise power of 1 watt and they're asking us to fan it into dB, what do? So we just multiply this y with 10 log of n0, which is in watt. We find the answer in dB. If now they ask us to find it in dB milliliter, what should I do? I will take this n0, which is 1 watt, which is watt in milliwatt, is 1000 milliwatt. Now if I want to find this in dB, it should be dBm. It will be watt again, it will be 10 log of this one here. The answer should be dBm. Okay, so what I'm trying to say, if you have enough power in watt, they ask you to find it into dB, you just multiply by 10 log. If you have it in milliwatt, that means it's dB milliwatt. Thank you for watching, and don't forget to subscribe. All the best for your exam. Thank you very much. Sorry for the late message. Cheers.